Picture this. Over 15 million crabs moving through sophisticated processing plants every single day, transforming from live marine creatures into premium seafood products worth more than $8 billion annually in global export markets. Imagine automated systems handling these delicate crustaceans with precision that rivals the most advanced manufacturing operations, while maintaining the quality standards that make crab one of the world's most sought-after luxury foods. What if I told you that modern crab farming has evolved from simple coastal operations into high-tech aquaculture enterprises that can produce over 50,000 pounds of premium crab meat per facility each year? Welcome to AgriCraft, where we dive deep into the most fascinating aspects of modern agriculture and food processing technology. I'm your host, and today we're exploring the incredible world of commercial crab farming and processing, an industry that represents the cutting edge of aquaculture innovation. From the carefully controlled breeding facilities where millions of crab larvae begin their journey, to the state-of-the-art processing plants where industrial machines transform these creatures into the premium products gracing tables in the finest restaurants worldwide, we'll follow every step of this remarkable agricultural transformation. All will be revealed in this video. The history of crab cultivation stretches back over 2,000 years, beginning with ancient Chinese farmers who first discovered they could raise crabs in controlled pond environments. What started as small-scale traditional farming has exploded into a massive global industry that now produces over 2 million tons of farm crab annually, with China alone accounting for nearly 80% of world production. This isn't just about traditional pond farming anymore. Modern crab aquaculture represents one of the fastest-growing sectors in global agriculture, generating revenues that exceed those of many traditional crop industries. The United States imports over $400 million worth of crab products annually, with much of this supply coming from sophisticated farming operations that have revolutionized how we think about marine agriculture. The economic impact of modern crab farming extends far beyond the farms themselves. Processing facilities, transportation networks, packaging operations, and distribution systems create employment for hundreds of thousands of workers worldwide. In Maryland alone, the crab processing industry supports over 12,000 jobs and contributes more than $600 million annually to the state economy. What makes crab farming particularly fascinating from an agricultural perspective is the incredible diversity of species being cultivated. Blue crabs dominate American markets, while mud crabs and swimming crabs lead Asian production. Each species requires completely different farming techniques, processing methods, and quality control procedures, creating a complex agricultural ecosystem that demands expertise across multiple disciplines. The scale of modern operations is truly staggering. Individual crab farms in China can contain over 5,000 separate ponds, covering more than 10,000 acres, producing upwards of 3,000 tons of live crab annually. These facilities utilize sophisticated water management systems, automated feeding equipment, and computerized monitoring networks that track everything from water temperature to oxygen levels across vast farming complexes. The transformation from traditional fishing to intensive farming represents one of agriculture's most dramatic success stories. Where wild crab populations once limited supply and drove prices beyond reach for most consumers, modern farming operations now provide consistent, year-round availability of high-quality crab products at accessible prices. This agricultural revolution has democratized access to what was once considered an exclusive luxury food. Let's explore how these remarkable operations actually function, beginning with the sophisticated breeding and cultivation systems that form the foundation of modern crab farming. The foundation of successful crab farming begins with understanding the complex life cycles and environmental requirements that these remarkable creatures demand. Unlike traditional livestock, crabs undergo multiple distinct developmental stages, each requiring precise environmental conditions and specialized care protocols. Modern crab breeding operations start with carefully selected broodstock, mature crabs chosen for their genetic qualities, disease resistance, and reproductive potential. These breeding facilities maintain thousands of adult crabs in controlled environments where water temperature, salinity, and oxygen levels are monitored continuously. A single female crab can produce between 1 and 4 million eggs during spawning season, providing the genetic foundation for massive farming operations. The larval stages represent the most critical phase in crab cultivation. Newly hatched crab larvae are microscopic and incredibly fragile, requiring water conditions maintained within extremely narrow parameters. Modern hatcheries utilize sophisticated filtration systems, temperature control equipment, and automated feeding mechanisms to nurture these tiny creatures through their complex metamorphosis from floating larvae to bottom-dwelling juveniles. Environmental requirements for crab farming vary dramatically depending on the species being cultivated. Blue crabs require brackish water environments with specific salinity levels that change throughout their development. Mud crabs thrive in freshwater pond systems with carefully managed dissolved oxygen levels. Each species demands unique water chemistry, temperature ranges, and habitat structures that must be precisely maintained throughout the growing cycle. The cultivation process typically occurs in specially designed pond systems that can range from small half-acre operations to massive industrial complexes covering hundreds of acres. These ponds are engineered with sophisticated water exchange systems, aeration equipment, and bottom substrates optimized for crab behavior and growth. Modern pond design incorporates everything from automated water quality monitoring to predator exclusion systems that protect valuable stock from birds and other threats. Nutrition management in crab farming requires understanding the natural feeding behaviors and dietary requirements of different species. Young crabs are fed specialized micro-diets containing essential nutrients for shell development and growth. As they mature, diets transition to formulated feeds that may include fish meal, plant proteins, and vitamin supplements designed to optimize growth rates and meat quality. Feeding systems in modern crab farms utilize automated equipment that can deliver precise amounts of feed to thousands of ponds on programmed schedules. These systems monitor feeding response, adjust portions based on growth rates, and ensure optimal feed conversion ratios that maximize production efficiency while minimizing environmental impact. Growth monitoring represents a critical component of successful crab farming. Unlike other livestock, crabs grow through a molting process where they shed their shells and rapidly increase in size. Understanding and predicting molting cycles allows farmers to optimize feeding schedules, adjust population densities, and time harvest operations for maximum yield and quality. Disease prevention and health management require specialized veterinary knowledge and sophisticated monitoring systems. Crab farms employ water quality specialists, aquatic veterinarians, and disease management protocols that prevent the outbreaks that could devastate entire operations. Modern facilities utilize everything from probiotic treatments to advanced water sterilization systems to maintain optimal health conditions. The care and management of juvenile crabs involves understanding complex social behaviors and territorial requirements. Crabs can be aggressive and cannibalistic, requiring careful population density management and habitat design that provides adequate shelter and feeding areas. Modern farming facilities incorporate artificial reef structures, hiding places, and territorial boundaries that allow maximum stocking densities while maintaining animal welfare. As crabs reach market size after months of careful cultivation, farmers must master the intricate timing and techniques required for successful harvest operations that maintain product quality while maximizing operational efficiency. The harvest stage in crab farming represents the culmination of months of careful cultivation and the beginning of the complex process that transforms live crabs into premium market products. Unlike traditional fishing operations that depend on seasonal availability and unpredictable catches, farmed crab harvest can be precisely timed to meet market demands and optimize product quality. Harvest timing in crab farming requires sophisticated understanding of growth cycles, molting patterns, and market conditions. Crabs are typically harvested when they reach optimal size and shell hardness, factors that directly impact meat yield and market value. Modern operations utilize growth monitoring systems and predictive modeling to determine optimal harvest windows that maximize both quantity and quality of the final product. The actual harvesting process varies significantly depending on the farming system and species involved. Pond-based operations typically utilize specialized draining techniques that concentrate crabs in collection areas where they can be efficiently gathered. These systems incorporate automated sorting mechanisms that separate market-ready crabs from those requiring additional growing time. Manual harvesting techniques remain important in many operations, particularly for premium products destined for live markets. Experienced harvest crews can evaluate individual crabs for size, shell condition, and overall quality, making real-time decisions about product grading and market destination. This expertise ensures that only the highest quality crabs proceed to premium processing lines. Mechanical harvesting systems have revolutionized large-scale crab farming operations. These sophisticated machines can process thousands of crabs per hour, automatically sorting by size and quality while maintaining careful handling that preserves product integrity. Conveyor belt systems transport harvested crabs through washing stations, size grading equipment, and initial quality inspection procedures. Transportation from farming facilities to processing plants requires specialized equipment designed to maintain crab viability and quality. Live transport systems utilize temperature-controlled trucks with sophisticated water circulation and oxygenation equipment. These mobile aquarium systems can transport thousands of live crabs across hundreds of miles while maintaining optimal survival rates and product quality. Many large-scale operations have invested in on-site processing facilities that eliminate transportation stress and maintain maximum product freshness. These integrated operations can process crabs within hours of harvest, ensuring optimal meat quality and extending shelf life for both domestic and export markets. The scale of harvest operations varies dramatically across different farming systems. Small specialty farms might harvest several hundred pounds weekly for local markets, while industrial operations process tens of thousands of pounds daily during peak harvest seasons. Regardless of scale, maintaining consistent quality and efficient processing remains the key to commercial success. Quality assessment during harvest involves evaluating multiple factors that affect final product value. Shell hardness, meat content, overall health, and size consistency all influence processing decisions and market pricing. Modern operations employ trained quality assessors who can rapidly evaluate these factors and direct crabs to appropriate processing streams. Seasonal harvest planning requires coordinating farming cycles with market demands and processing capacity. Peak harvest periods must align with processing plant availability, transportation schedules, and market demand cycles. This coordination requires sophisticated planning systems that integrate farming operations with complex supply chain requirements. As harvested crabs enter processing facilities, they encounter industrial systems specifically designed to transform these complex crustaceans into the diverse range of products that supply global seafood markets. The processing stage represents where traditional seafood handling meets cutting-edge food processing technology. Modern crab processing plants are engineering marvels designed to handle the unique challenges these crustaceans present while maintaining the highest standards of food safety and product quality. Upon arrival at processing facilities, live crabs undergo immediate quality inspection procedures that determine their processing pathway. Trained inspectors evaluate each batch for shell condition, meat content, and overall vitality. This initial assessment separates premium crabs destined for whole crab markets from those that will be processed into picked meat products. The sterilization and cleaning protocols in crab processing plants exceed standards found in most food processing operations. Workers undergo extensive hygiene procedures, including multiple sanitizing stations, protective clothing requirements, and health monitoring protocols. Processing areas are maintained under strict temperature and humidity controls with automated cleaning systems that sanitize equipment between production runs. The initial processing begins with stunning and cooking procedures specifically designed for crustaceans. Modern crab processing plants utilize steam cooking systems that can process thousands of crabs per hour while maintaining precise temperature and timing controls. These industrial machines ensure consistent cooking throughout the crab while preserving optimal meat texture and flavor characteristics. Automated systems handle the complex task of shell removal and meat extraction. These sophisticated machines utilize high-pressure water systems, mechanical crackers, and precision cutting equipment to separate valuable meat from shells with minimal waste. The technology behind crab picking machines represents some of the most advanced food processing engineering available, capable of extracting meat from complex shell structures that once required entirely manual labor. Conveyor belts transport products through multiple processing stages, each optimized for specific product types. Whole cooked crabs move through packaging lines while picked meat products undergo additional sorting and quality control procedures. These automated systems maintain consistent processing speeds while allowing for real-time quality adjustments and product customization. The sorting and grading procedures for crab meat represent some of the most sophisticated quality control systems in the seafood industry. Meat is categorized into multiple grades based on size, color, texture, and shell content. Automated optical sorting systems can identify and separate different meat grades at speeds impossible with manual labor, ensuring consistent product quality across large production volumes. Temperature control throughout the processing plant is critical for both food safety and product quality. Different processing areas maintain specific temperatures optimized for particular procedures. Cooking areas operate at high temperatures while packaging areas are kept at near freezing conditions to ensure product stability and extended shelf life. Modern crab processing plants also incorporate specialized equipment for handling the diverse range of products derived from these crustaceans. Shell processing systems extract valuable calcium-rich materials for animal feed and agricultural applications. Even the cooking water is processed to recover valuable proteins and minerals that would otherwise be waste products. Quality inspection continues throughout every stage of processing, with trained quality control specialists monitoring production lines continuously. Products are tested for bacterial levels, temperature compliance, foreign matter content, and consistency with established quality standards. Any products that fail to meet strict quality requirements are immediately diverted to alternative processing streams or disposed of according to food safety protocols. The industrial machines used in modern crab processing represent significant technological investments. Individual processing lines can cost upwards of $10 million to install and configure, with complete processing facilities representing investments of $50 to $100 million. These sophisticated systems are capable of processing thousands of pounds of crab per hour while maintaining quality standards that exceed those achievable through traditional manual processing methods. Following the intensive processing procedures, crab products move into sophisticated packaging and distribution systems designed to preserve quality while meeting the diverse requirements of both domestic and international markets. The packaging systems used in modern crab processing operations must accommodate the unique challenges presented by these perishable seafood products. Automated packaging lines utilize multiple packaging formats simultaneously, switching between vacuum packaging for premium picked meat, modified atmosphere packaging for whole-cooked crabs, and specialized containers for live crab shipments. Vacuum packaging represents the primary preservation method for premium crab meat products. These automated systems remove all air from packages while injecting nitrogen or carbon dioxide to create environments that prevent bacterial growth and oxidation. The packaging materials are specially designed multi-layer films that provide exceptional barrier properties against oxygen and moisture while maintaining flexibility during frozen storage and transportation. Modified atmosphere packaging systems create customized gas environments optimized for specific crab products. Whole-cooked crabs benefit from carbon dioxide-enriched atmospheres that extend shelf life while maintaining optimal color and texture. These systems can adjust gas compositions in real time based on product type and intended storage duration. Labeling systems in crab processing facilities must accommodate complex regulatory requirements across multiple international markets. Products destined for European Union countries require different labeling than those headed to Asian markets. Automated labeling machines switch between label formats instantly, applying appropriate nutritional information, origin certification, allergen warnings, and traceability data to each package. Cold storage facilities and crab processing plants maintain multiple temperature zones optimized for different products and storage durations. Fresh products are stored at temperatures just above freezing, while frozen products are maintained at -18 degrees Celsius. These storage systems incorporate sophisticated inventory management systems that track product age, batch information, and quality parameters throughout the storage period. The distribution networks for crab products span the globe and require expertise in international shipping regulations, cold chain management, and quality preservation during extended transportation. Premium live crabs might be airshipped to restaurants within 24 hours of processing, while frozen products travel through conventional refrigerated shipping networks that can take weeks to reach final destinations. Quality control procedures extend throughout the packaging and distribution process, with products tested regularly for bacterial levels, temperature compliance, and package integrity. These tests ensure that products maintain safety and quality standards throughout their journey from processing plant to final consumer, regardless of transportation method or destination. Traceability systems in modern crab processing utilize advanced tracking technology that allows individual packages to be traced back to specific farms, harvest dates, and processing batches. This level of traceability provides critical information for food safety management while helping processors quickly identify and address any quality concerns that might arise in the distribution chain. Shipping logistics for crab products require specialized knowledge of international trade regulations and seafood import requirements. Different countries maintain varying standards for crab product imports, and successful operations maintain expertise in navigating these complex regulatory environments. This knowledge is essential for accessing premium international markets that provide the highest returns for quality crab products. Automated packaging systems represent significant technological investments for crab processors. Modern packaging lines can package thousands of pounds of product per hour while maintaining precise portion control, consistent package appearance, and reliable seal integrity. These systems incorporate vision inspection equipment that identifies packaging defects and automatically rejects substandard packages before they enter the distribution system. The packaging and distribution systems represent the final critical link in the crab farming value chain, ensuring that the quality and freshness built into products throughout the farming and processing stages reaches consumers in optimal condition while meeting the logistical demands of global seafood markets. Beyond the primary meat products, crab processing operations generate numerous valuable byproducts that contribute significantly to overall economic viability, while demonstrating the comprehensive utilization possible in modern seafood processing. Crab shells represent one of the most valuable byproducts in the industry, containing high concentrations of calcium carbonate and chitin that command premium prices in multiple markets. The shells are processed through specialized grinding and separation systems that produce different grades of shell meal for various applications. Finely ground shell meal serves as a valuable calcium supplement in animal feeds, while coarser grades are used in organic fertilizer formulations that improve soil structure and provide slow-release nutrients. The chitin extracted from crab shells has become increasingly valuable in biotechnology and medical applications. Modern processing facilities utilize chemical extraction processes that separate chitin from calcium carbonate, producing pure chitin that sells for thousands of dollars per ton. This biopolymer is used in wound dressings, dietary supplements, and biodegradable plastic applications, creating high-value revenue streams from what was once considered waste material. Crab cooking water, which contains dissolved proteins, minerals, and flavor compounds, is processed through concentration and drying systems to produce valuable flavor enhancers and protein supplements. These concentrated extracts are sold to food manufacturers for use in soups, sauces, and seasoning products, capturing value from every component of the processing operation. The processing of crab organs and secondary tissues provides additional revenue opportunities through specialized processing lines. Crab roe, when properly processed and graded, commands premium prices in Asian markets where it is considered a delicacy. Hepatopancreas and other organ meats are processed into paste products that serve as flavor bases for traditional seafood dishes. Even the wastewater from crab processing facilities is treated and processed to recover valuable components. Modern treatment systems extract proteins and minerals from wastewater while producing treated water that meets environmental discharge standards. Some facilities have invested in biogas production systems that convert organic waste into renewable energy for powering processing operations. The comprehensive utilization of crab byproducts requires sophisticated processing equipment and specialized knowledge of multiple markets. Shell processing lines utilize grinding, screening, and magnetic separation equipment to produce consistent grades of shell meal. Chemical extraction systems for chitin production require expertise in processing chemistry and environmental compliance. Quality control for byproducts maintains the same rigorous standards applied to primary products. Shell meal is tested for calcium content, particle size distribution, and microbial levels. Chitin products undergo purity analysis and molecular weight testing to ensure they meet specifications for pharmaceutical and industrial applications. The markets for crab byproducts continue expanding as new applications are developed for these materials. Research into chitosan production, biodegradable plastics, and nutraceutical applications creates new revenue opportunities for processors willing to invest in specialized processing equipment and market development. The economic impact of byproduct utilization can represent 20 to 30% of total revenue for well-managed crab processing operations. This additional income stream helps offset processing costs while contributing to environmental sustainability through comprehensive waste utilization. Modern crab processing facilities design their operations around complete resource utilization, incorporating byproduct processing equipment into their initial facility planning rather than treating it as an afterthought. This integrated approach maximizes economic returns while minimizing environmental impact. When it comes to culinary applications, crab represents one of the world's most versatile and prized seafood ingredients, supporting a diverse range of food products and preparation methods that span cultures and cuisines globally. Crab meat offers exceptional culinary versatility with distinct characteristics that vary significantly between different species and processing methods. Blue crab meat provides sweet, delicate flavors that make it ideal for applications where subtle seafood taste is desired. Dungeness crab offers firmer texture and more pronounced flavor that works well in dishes requiring stronger seafood character. Each variety brings unique qualities that professional chefs and food manufacturers utilize in specific applications. The nutritional profile of crab meat makes it an exceptional protein source that appeals to health-conscious consumers. Crab meat contains over 20 grams of protein per 3-ounce serving while providing less than 1 gram of saturated fat. The meat is exceptionally rich in vitamin B12, zinc, and selenium, while providing significant amounts of omega-3 fatty acids typically associated with heart health and cognitive function. Processing methods significantly influence the final nutritional and culinary characteristics of crab products. Fresh-picked meat maintains optimal texture and flavor but requires careful handling and short shelf life management. Pasteurized crab meat undergoes thermal processing that extends shelf life while maintaining nutritional value and most flavor characteristics. Frozen crab products sacrifice some texture qualities but provide extended storage capabilities and consistent availability. Professional food service operations utilize crab products in applications ranging from simple preparations that highlight natural flavors to complex dishes where crab serves as a component in elaborate preparations. Crab cakes represent one of the most popular applications, requiring specific meat grades and binding techniques that maintain crab flavor while providing proper texture and cooking characteristics. The meat grading systems used in crab processing create products optimized for different culinary applications. Jumbo lump meat commands premium prices for applications where large, intact pieces are desired. Backfin meat provides good flavor and appearance for mid-range applications. Claw meat offers strong flavor at lower cost for applications where appearance is less critical. Preparation methods for different crab products require understanding the unique characteristics each processing method imparts. Live crabs require immediate cooking and handling to maintain optimal meat quality. Pre-cooked products need careful reheating to prevent overcooking that toughens meat texture. Frozen products benefit from controlled thawing processes that preserve meat structure and minimize moisture loss. The development of value-added crab products has expanded market opportunities while creating new applications for different meat grades. Crab bisques, spreads, and prepared entrees utilize processing techniques that maximize flavor while accommodating automated manufacturing processes. These products allow manufacturers to utilize mixed meat grades while producing consistent, high-quality prepared foods. Nutritional analysis reveals that crab meat provides exceptional mineral content, particularly copper, which is essential for immune system function and connective tissue development. The meat also contains significant amounts of phosphorus and potassium, while maintaining very low sodium content compared to many other seafood products. From an environmental perspective, modern crab farming represents one of the most sustainable approaches to aquaculture, demonstrating how intensive farming systems can work in harmony with natural ecosystems while producing high-quality protein efficiently. The environmental impact of crab farming compares favorably to most traditional livestock operations and even to many other forms of aquaculture. Crab farming requires no deforestation, minimal freshwater usage, and creates habitat that often supports diverse aquatic life beyond the target species. Well-managed crab farms can actually improve local water quality through biological filtration and nutrient processing. Water usage efficiency in crab farming exceeds that of most agricultural operations, Recirculating aquaculture systems can produce thousands of pounds of crab while using less water than required to produce equivalent protein from traditional livestock. Modern farms utilize closed-loop water systems that filter and reuse water continuously, minimizing both water consumption and effluent discharge. Carbon footprint analysis of crab farming reveals remarkable efficiency compared to terrestrial livestock operations. Crab farming produces significantly less greenhouse gas emissions per pound of protein than cattle, pig, or poultry operations. The absence of methane production and minimal feed conversion requirements contribute to this environmental advantage. Sustainable farming practices in crab aquaculture include integrated multi-trophic systems where crab farming is combined with other aquatic species that utilize different nutrients and occupy different ecological niches. These polyculture systems maximize production efficiency while creating more stable and resilient farming ecosystems. Modern crab farms actively participate in habitat restoration and environmental monitoring programs. Many operations incorporate native vegetation plantings, water quality monitoring, and wildlife habitat creation into their facility design.